Welcome after a very long time to the Department of Electrical Engineering. Today we will study the second order system network. Here is the second order network system, and this is the DSO. So we will study today the second order system. This is the second order system network, series RLC network, and we will see the response of the when we will give the input, square input or sinusoidal input, and we will see the response like this on the DSO. So we will measure different things, like we will measure TP, that's the peak time, and T naught, also the rise time, peak time. So we will calculate that on DSO. So now we will check by connecting the signal here, the input signal. The signal we will give like this, input signal, and we will see the response, how the second order system will look like on the DSO. So now we will see the response on the DSO. So we will connect the probe here, and we will see the response, how the second order system response will be. Connect the probe and I will see the response. See, this is the ground and this is the response. Look the response here. This is the second order system, and I think here now you can see the zeta is more, and it is under damped system, and here are more oscillations. I will stop it and I will show it. Look, on one signal I will show it. Look, the oscillations are more here. Now we have to see the signal is like this, and we have to measure first I of TP. I of TP will be measured here. How you will measure I of TP? So first of all, you have to see what is the value of the one box, that is given here, that is channel 1, that is almost 500 millivolts, that is given here. So one box is 500 millivolts, that this peak is almost up to this point, that is we say it is 1.8 up till here, and you have to see where is the peak. So 500 into 2 almost into 1.9, that is almost 0.9 millivolts, you can say, that is I of TP. After I of TP, you have to measure TP. So TP you have to measure from here to here. It's peak, but from here to here, because it's the time scaling. So that is 1 millisecond. So it is here up to here, that is half, 0.5 milliseconds it will be. And after that you have to measure T naught, that is the first zero crossing. So where the first zero crossing is, that is here. So how much it will be? It will be one box and half of the box. That is one box is 1 millivolts, and it will be half, that is 1.5 milliseconds it will be. Okay, 1.5 milliseconds it will be. So I will show now how you have to calculate the other things. As you have already calculated I of TP, you have already calculated TP and T naught. We know that T naught by TP is pi by theta, and now you will get, because T naught and TP you are knowing, pi is constant, so you will get theta. Theta will be some value will be there, and then you will calculate theta, and you will put that theta in this equation, tan inverse of under root of 1 minus zeta square divided by zeta, and you will squaring mathematical calculation, and you will get this zeta, value of this zeta here. It is almost 0.1. After that you will calculate omega n by the formula omega n is pi divided by T naught under root of 1 minus zeta square, and when you will calculate omega n, you know the value of C is given on the equation, that is I of TP divided by omega n e raised power this, and that will be, so you will get the value of the capacitor here. So after the value, you will get the value of the capacitor, you have to get the value of the inductor. So now you will put, you know the value of the capacitor, you know the value of the omega n, you can get now the L, that is inductor. Now you had got the inductor value, now you have to get the resistance, how much will be the resistance. Now you know L, you know C, you will put the value, you know zeta already, so you will get R. So now you can repeat the process by increasing the value of the zeta. Now I will increase the value of the zeta here, and you will see the response, what will happen to the response, and you can measure the values again and again. Now you can check how I will increase the value of the zeta. Look, I will now increase the value of this zeta. Look, the response, the damping is getting lesser and lesser here. I will again increase the, look, the damping is getting lesser and lesser. So you can change the zeta here, and you can see the response that zeta is getting lesser. The damping is getting lesser and lesser. Now I will again decrease the zeta. Look here, and you will see the response here. Again the oscillations will increase. oscillations will increase, and you can calculate different values. Now because when the zeta will vary, obviously I of tp will vary, t naught will vary, and all the values L, C, R and will vary. So by this method you can you can vary the zeta, and you can calculate the value L, R and C and different parameters. So you can design RLC circuit.